Hi, my name is Muhammad Imam Fahmi bin ZAMRISHAM. My matric number is B0920103060. Okay, we have 4 group member. My first member name is Anas, and second AZALINA, and third LAILY. In this assignment, my group decide to explain about control system of vehicle suspension. First of all, I would like to talk about vehicle suspension system generally. Suspension system is a protective lattice of shock absorbing components such as spring and dampers. As we know, car suspension help ensure that your drive is safe and smooth by absorbing the energy from various road bumps and other kinetic impacts. Furthermore, it helps your tires stay in contact with the road by increasing tire friction. Okay, based on this picture, you can see the location of shock absorber, spring, car frame, and steering link. Okay, this picture can easy to understand, and you can know where the location of this part. Next, I would like to talk about simple suspension control system to easy understanding. When you encounter a bump on the road, it forces your wheel to move up and down, but larger road bumps or surface impression can transfer quite a bit of energy. If you don't have a suspension, all the energy transmit into your car frame. Okay, next, the car suspension important to absorb the energy transfer through your car wheels, and then suspension help your car cabin to ride atop the suspension smoothly. Second order system has 2 poles that, depending on component values, display damp or per oscillation. The response of order system has 4. First, overdamp. Second, critically damp. Third, underdamp. And for the last, undamp. For this assignment, we get underdamp, so you can refer the graph given. Okay, next, system modeling. So you can see the picture. Based on the right side, we have a complete system modeling. The arrow show M1 and M2 is a mesh, and arrow also show spring and absorber. Okay, after that, this is a transfer function that we use. 13,200 is spring constant, divided by 110 S square is a mesh, plus 330 S is a damper, plus 13,200 spring constant. Then we calculate, we get the final equation. This equation ready to using for MATLAB software. Okay, next, this is a block diagram for control system of vehicle suspension. Okay, you can see the block diagram show the input and output. The input is force Fs, and Gs transfer function, and Ys is output.
Assalamualaikum and good day to Madam Shahazati. I am Rozali ARFAH, and I will be explaining about the calculation results of the transient response characteristic, which are the peak time, the settling time, and the percent of the overshoot. So before we start calculating the response performance specifications, we first need to know the meaningful specs for second order system, which are the natural frequency and the damping ratio. The natural frequency is actually the frequency of oscillation of the system without the damping. Meanwhile, the damping ratio is the ratio between exponential decay frequency and the natural frequency. So, where do we get these values? Through the transfer function. So, let's look at the transfer function of our system. So, this is our transfer function. We get the values by comparing our transfer function to the general equation. Then, we equate whichever that may apply to the function, and boom, we get the values. Not forget to mention the value of our system's damping ratio shows that our system are underdamped because the value of our damping ratio is in between of 0 and 1. So next, the time required to reach the maximum peak, or also known as the peak time, can be calculated as shown. For the settling time, which the time required for the transient damped oscillation to reach and stay within plus minus 2% of the steady state value can be calculated as shown. And as for the percent of overshoot, we can get the value using the equation as follows.
Okay, from the equation that we get, so we use MATLAB to generate the data. Okay, first we key in. Okay, and then we put the transfer function and put the numerator. Okay, next we put the denominator. Okay, don't forget the semicolon. Then we use step plot to generate the graph. And we use step info to generate the data. Okay, after we got all these equation, so we can run this and we can get the graph. You can see here. Okay, you can see the peak response, rise time, settling time, present time, and the steady state. Okay, and then it also tell us below here the rise time, transit time, and all the info below here by using the equation step info.
Now, if we compare the calculation results to the response simulation, we can see the values are slightly different, in which I believe it is due to the initial decimal point taken for calculation. Overall, it has no big difference that may require to manipulate the values accordingly. Thank you.
Assalamualaikum and good day. I am AZALINA binti ANUAR and I will continue the presentation with explanation on how do we get the state space representation. Since we already have the transfer function GS, in order to get the state variables, we are using the phase variable method. The state variables are phase variable when each subsequent state is defined to be the derivative of the previous state variables. Consider the input f and the output is y described by the transfer function. First, the transfer function written as the ratio of the Laplace transform of the output and the Laplace transform of the input with all the initial conditions assumed to be 0. Then, we obtain the differential equation by taking the inverse Laplace transform. After that, we choose the state variables as successive derivative. All the above definitions are now replaced into this equation. From the last relation and the definition of the phase variables, we got the state equation in the phase variable form and also the output equation. This is the state space model in the matrix vector form. So, this is the state space we obtain.
Okay, now for the stability of the suspension system. Okay, the stability that we get by MATLAB is we get at the left hand side. So we get the left hand side at the top and at the bottom. If by using MATLAB we get the stability at the left. That means it is a stable system. Okay. Also by using Ralph-Swiss, we calculate and we get all the positive
real number.
It means it is a proven this system is a stable system. Okay, this one I use the MATLAB equation. This is the equation and the below one is the answer. And the Ralph-Swiss answer is also proven that it's stable. So the conclusion for the stability is this system is stable.
Okay, next we're calculating the steady state error.
For our system, we are using a closed loop system, so we can calculate the steady state error using the final value theorem. Now, let's plug in the Laplace transforms for some standard input and determine equations to calculate steady state error for the system. We need to do three equations. The first one is step input, and we got the answer is a constant value. The second one is ramp input. The answer is infinity. And lastly is parabolic input. The answer also infinity. So we confirm that the system is type 0 because the value of every steady state value are fulfill the requirements where the step unit is a constant value, ramp input and the parabolic input are infinity value. In the nutshell, we confirm that our system is in the stable state. It is due to pole's location. From the calculation and the simulation value of the damping ratio, our system is underdamped. It is due to the value of the damping ratio is in between 0 and 1. That's it. Thank you.